So let's generalize this graphing a little bit. We've seen that an exponential function has this shape that we've got going on here. It grows quickly, it grows exponentially, and one that will is the most basic is y equals 2 to the x, something like this. And as that base number, we're changing the base here. As that number gets larger, this gets steeper. Okay. And as that number gets less than 1, once we cross 1 here, okay, we have exponential decay. So in this base number, if we have 0.73 to the x power, that's this exponential decay. All right, so on and so forth. All right, and 0.24, that's like 1/4 to the x power. Okay, now notice these are always going through 0, 1. Well, what happens when we put a number out here in front? So if we take, and let's put a number, let's call it A here, and we'll add a slider for A. Okay, well, let me go put this back to 2 there, all right? So now A is this number out in front, okay? So notice A is not under the exponent, so the exponent does not affect that, okay? So let's watch what happens. So as A moves to the right, that's affecting this y-intercept. In fact, notice this, we got 9.7. Look where the y-intercept is, 9.7, okay? So that is the y-intercept. Okay, so that value is the y-intercept. So it's changing there. We have 1.6, and that's the y-intercept. Okay, we've got, 0. That takes it down to 0 there. Okay, and what happens when it goes negative? When that A value goes negative, now remember the B value cannot be negative. But when A is negative here, it flips it upside down. So if we're multiplying by a negative number out in front, it's going to flip it upside down. And if that's just plain old -1, all right, so there's like, so this shape right here is the same shape as 2 to the x, but it's flipped upside down. Notice this, we go right 1, down 2, because 2 to the first is 2. Right 2, down 4, because 2 to the second is 4, but we're making it negative. All right, so this right here is y equals -2 to the x. All right, so negative, really it's the better way to write it might be like this, -2 to the x. But it's important to understand this, that is the same as y equals -2 to the x. This negative sign right here is not getting affected by the x, okay, because it's not inside parentheses, okay? Only that's 2 to the x made negative. All right, important note there. All right, so we'll take that A out of there. We're not worried about that anymore, but that's what that does. So how about now, let's go ahead and let's change what's in the x up here. And so if we do x plus, maybe we'll call this h, all right? And we'll get a slider there. Okay, so when we add a number like +5, +6, +7, +8, notice the whole thing is sliding left. And when we subtract, the whole thing is sliding right. So this h value is our left and right control, just like with the quadratics, with the parabola, all right? That's the idea there. Let's leave it at 0. What happens if we add a number outside? Let's add k. And let's make that a slider. So if we add a number outside, there k is 1. Okay, oops. K is 1, k is 2, 3, 4, 5. Okay, that moves the whole thing up. And if it's negative, it moves the whole thing down. The shape is not changing. It's just moving up and down. So k goes up and down, and h goes left and right, just like with the parabola. Now notice this. An important thing here is to see this is the asymptote. The asymptote here is at 0, all right? So asymptote's going right along here. Now, if we take this k number and move it up, now we have That's 5.2. Let's see if I can make it right on 5 there. Oh, doesn't want to go. Anyways, that is the asymptote, all right? So whatever this lands on, if it'll be nice, which is not being very nice for me, okay, that is the asymptote. So right here, there's an asymptote right here. It's never going to touch the value, in this case, y equals, because I just got 5.1, 5.1. Okay, so with all of that there, we can generalize what's going on, and we can get some graphs out of this. So here's what's going on in general. We know that if we have this function here, that the a value, that's going to be our initial value or our y-intercept. Okay, so our initial value or our y-intercept, because when, all right, so that, now we got to be careful. If h and k are 0, then that's our y-intercept. So h and k have something to say about it also. But a can also flip the graph, or a better word than that is to reflect across the x-axis. That b value is the base, okay, and that affects its shape. Okay, we know that if b is greater than 0, it's exponential growth. All right. And if b is less than 0, that's exponential decay. So that's the idea of b. Then the h and k is our left and right. So h is going to move it, well, h's, it is, left and right. Left, if we have x plus something, so plus moves it to the left. I'll put a plus h. And then it's right if you end up with an exponent that says x minus h. Right? Then the k value is going to move up for a positive k value, and then it's going to move it down for a negative k value. All right, so let's see how this works. So we want to graph this function y equals 2 to the x plus 3 minus 5. And we want to compare it to the graph 2 to the x. So if we think about y equals 2 to the x, that should be a fairly familiar graph after we've done a few graphs, 2 to the x. We know that goes through 0, 1. I'm just going to put some points here. 1, 2, 2, 4. By the way, we should put some numbers on our axes here, at least one number on each axis. And then as we go to the left, it's going towards the axis. Okay, so there's some points. I don't want to put any more there. I'm not going to actually draw it in, but that gives us kind of a view. All right, so that's y equals 2 to the x. Well, what is going to be different with this graph? Well, the plus 3 there is going to move it left 3. And the minus 5 is going to move it down 5. And in fact, since it's going down 5, the asymptote is going to be at y equals negative 5. That's going to be the asymptote. So the floor, an asymptote's like the floor here, is going to be down here at negative 5. So when we're graphing this, what we want to do is, here, this was centered on the origin right here. Okay, everything was related to that origin. Well, what we need to do now is just realize that it's moved down 5 and left 3. I'm going to come over here left 3, and I'm going to put a little vertical line. That is not the axes, but think of this like the new origin. And now if I look at these green axes, these green lines, let me just, I'm going to pretend I'm going to be thinking y equals 2 to the x. and we're going to graph 2 to the x here. Well, if this little yellow dot really was the origin here, then 2 to the x would mean I'm going to graph at 0, 1. And then I'm going to graph it at 1, 2. That would be like right here. And then we're going to graph it at, I'm going to go from the origin, right 2, up 4. And then going to the left of the origin, if this was the origin, to the left we're going to be cutting in half, cutting in half. Oops, that's not half. Cutting in half, going down, down, down towards the asymptote. So that's enough there to get a decent little picture of where the graph is. So all we did was we kind of re-centered the graph. So using what we know about how it moved, I just took this shape that I'm familiar with, and instead of centering on 0, 0, I centered on this point down here, which is left 3, down 5. And there we are. Okay, always should draw in this asymptote. Okay, so that's how those transformations can help us to get another graph pretty quickly and easily. So we're going to jump over some of those extra graphs there. That should hopefully give us an idea there. But one more thing to that we need to cover is compound interest. So when we're solving or we're working with exponents, we have some compound interest. Compound interest is what happens in the bank. All right. So when you go to the bank and you put your money in the bank, they give you a little bit of interest every year. And what happened is back in the past, oh goodness, in 100 years ago, they would just give you some interest once a year. Okay, that would be compound yearly. Okay, and so we have different ways of compounding. And so if we compound yearly, well, that obviously means 1 time per year. So they would pay you your interest 1 time per year. Okay. Well, if what happened was, another bank said, well, you know what? That bank down the street is giving you interest once a year. All right, but we're gonna give you a better deal. We're gonna give you interest every month. Okay, so we'll go monthly. Well, I kind of skipped it. The next jump probably would be quarterly. Quarterly means 4 times per year. Okay, and so we're going to give you interest 4 times a year. Well, but here's the thing. This bank is going to give you, let's say, 4%. Let's just pretend that the interest rate was 4%. That was the offer. Well, they'll give you 4% once a year. But we'll give you 1% 4 times a year. All right? So you're going to get your 4%, but we're going to give you a little bit throughout the year. And what happens is once that little bit goes in your bank account, it starts earning money. Okay? And so quarterly starts to earn a little bit more money, as we'll see here in a second. And then, another bank said, well, wait a minute. We'll give you interest monthly. Okay, monthly. That means 12 times per year every month. All right, so we'll give you some interest 12 times per year. Okay, and we'll take that 4%. 4% divided by 12 is 1/3%, so that's like 0.33%. All right. Now, the formula that helps us calculate this is our compound interest formula, and here it is. All right, and what this says is this: we're going to take P, the principal, and we're going to multiply that by 1 plus the rate, maybe it's 4%, divided by the number of times that you're going to get it every year. So if it was 4% and we're going to give it to you quarterly, then 4 divided by 4 would be 1%. All right. So let's look at a little quick example. Let's say you invest, you put in the bank $1,000 at, let's say, that 4% interest. Okay. And it's compound monthly. Okay. Compound monthly. All right. Monthly, let's say for whole 5 years. How much money will you have? All right. Well, here's how the formula works. We're going to take A is the amount that we have at the end of the time. P is 1,000. That's how much we put in. 1 plus the interest rate is 0.04 divided by the number of years, or number of times per year. N is 12. And we're going to raise it to the 12 times 5 because we're going to get 5 years, 12 times per year. That's 60 interest payments. All right? Well, this is just to solve this. It's just a matter of getting our calculator out here. And we're going to just punch in the calculator. So we have, let's see, 1,000. Calculator work right here. And we've got 1 plus 0.04. Got to change it into a decimal. Remember, when you change a percent to a decimal, you move the decimal point 2 places, divided by 12. And we will raise that, got to get close out parenthesis, to the 12 times 5, or 60th power. So that means you're going to have $1,220.99. Actually, that 99.996 is going to round up to 1. So that's how much you'll have at the end of those years, okay? So that's how the compound interest formula works. Okay, let's look at one other important investigation here. Let's say that we had $1 that we invested, and we're going to get 100% interest rate. No one's ever going to do that, but let's just say. So, and it's going to be for 1 year. Well, that gives us this equation here. We're investing $1, so P is $1. And it's going to be 100%, which is 1.0, divided by N, the number of times it is compounded. It's for 1 year, so our T is 1. Now, we want to watch what happens when N gets bigger and bigger and bigger. Okay, so let's investigate. We get a very important result that we're going to use, that is used a lot in mathematics here. Okay, let's get my calculator to work here. There we are. All right. So we'll say we have 1. Let's get some parentheses here. So here I've entered the function, and right now I have it as set at 1. So if N is 1, so we get that interest rate once a year, then we will double our money. 1 plus 1 over 1 to the 1 power. That is 2. Now, if we get it twice a year here, so let's see if we can bump this. Well, let's kind of quick jump. Say we jump that to whatever I can land on here. 10. Okay. Now it's kind of a big jump. All right. So if we want to jump this to, let's make this 10. Okay, there we go. All right. So if I do it twice a year, then I'll end up with $2.25 at the end of the year. So that's if I got interest twice a year. If I got interest 3 times a year, $2.37. 4 times a year. Okay, this is quarterly. I'd end up with $2.44. Okay. If I got it 6 times a year, every other month, I'd have $2.50. If I got it 10 times a year, okay, it's almost monthly. It's about $2.50. So what happened is banks kept saying, well, I'll give it to you. I'll give you every day. Let's go to every day. So 365 times a year, you're going to get your interest rate, but you only get a little bit of it. Well, you're going to walk away with $2.70. And then people say, well, you know what? I'll give it to you every second of the day. All right, you'll get. Let's just use our computers to calculate this, and you'll get a little bit like every second. Well, what happens as we divide that year up into more and more and more? Maybe you'll get it. If I give you interest 4,000 times a year, you'll have $2.71 at the end of the year. If we give you interest, 9,000 times a year, well, notice that this number is getting really close. It's not changing much. Even if I let me put a few more zeros in here, make my slider go up a little bit further. Okay, my slider goes up to 10 million now. Okay, and watch that number. So the bigger that n gets, the number doesn't actually change. Okay, so this is getting really close to a number. It's 2.71828, and that is a number that we call E. All right, we call it the natural number. It's an irrational number, a lot like pi. So this number, as n gets larger and larger and larger, this number goes to 2.71828. Okay, and we have a name for that. We call that pi, or E, sorry. It's like pi. Pi is 3.14159. You've seen that before. Well, this is called the natural number, or Euler's number, 2.71828. It shows up in lots of places, especially in things related to algebra and calculus. Okay, so we're going to see this graph here. We're going to want to graph e to the x, which is really just 2.71828. So e to the first is about 2.7. E to the 0 is like anything to the 0, which is 1. So this graph is really just, it's going to be real close to 2 to the x, but it's going to be up here at 2 to the 2.718. So it's going to look something like that. So there is y equals e to the x. And then if we do e to the negative x like this, well, it's going to be the exact reverse. E to the negative x is going to go up like this, close to 2 to the x, or negative x, but it's going to be that. So there's y equals e to the negative x. All right, well, there's a little background there to e to the x. We'll see that more in the next lessons. And we got our compound interest formula that we'll be using as well. And one last thing to tie this together. So what happens is this. If you want to give interest every instant, we have what we call the instantaneous interest formula. Okay, instant interest formula. And that is A equals the principal to the e to the RT power, where e is that 2.71828. Okay, that's compound continuously. That's a more common term. Compound continuously. Okay. Okay. So that is our compound continuously giving interest all the time, every instant formula. So hope that helps. We'll work some more on some graphing there, and also with some of that equation solving next time.